Section 10.4, Markov chains. Suppose a physical or mathematical system undergoes a process of change such that at any moment it can occupy one of a finite number of states. Suppose that such a system changes with time from one state to another, and at scheduled times the state of the system is observed. If the state of the system at any observation cannot be predicted with certainty, but the probability that a given state occurs can be predicted just by knowing the state of the system at the preceding observation, then the process of change is called a Markov chain or Markov process. If a Markov chain has k possible states, which we label as 1, 2, etc. through k, then the probability that a system is in state I at any observation after it was in state j at the preceding observation is denoted by Pij, and it is called the transition probability from state j to state I. The matrix P equal to the Pij entries is called the transition matrix of the Markov chain. Let's do an example. Let's say we have a car rental agency that has 3 rental locations denoted by 1, 2, and 3, and a customer may rent a car from any of the 3 locations and return the car to any of the 3 locations. The manager finds that customers return the cars to the various locations according to the following probabilities. So right over here we have our matrix P. Find the probability that a car rented from location 3 will be returned to location 2, and the probability that a car rented from location 1 will be returned to location 1. So first, the probability that a car rented from 3 is returned to 2 is equal to 0.6, right? It's taken from 3 and it returns to 2. So by our matrix, it equals 0.6. Now the probability that a car rented from 1 is returned to 1 is right over here. We look at 1 must be 0.8. By reviewing its donation records, the alumni office of a college finds that 80% of its alumni who contribute to the annual fund 1 year will also contribute the next year, and 30% of those who do not contribute 1 year will contribute the next. What is the transition matrix? So in this case, we have P equals, well, if 80% of the alumni who contribute 1 year also contribute the next year, we could use 0.8 for this top left entry. That's like the 1, 1, where it's the same for both, which makes the one underneath it 0.2 for the ones who contribute 1 year and then don't contribute the next. And then we have the 30% who contribute, who do not contribute 1 year but will contribute the next. And then last but not least, this last entry must be then 0.7 because it must be the 70% who don't contribute either year. And that'll be our transition matrix P. The state vector for an observation of a Markov chain with k states is a column vector x whose ith component, xi, is the probability that the system is in the ith state at that time. If P is the transition matrix of a Markov chain and xn is the state vector at the nth observation, then xn plus 1 is P times xn. So to find the next state vector, we just have to multiply by the transition matrix. How about we now use the transition matrix from example 2 to construct the probable future donation record of a new graduate who did not give a donation in the initial year after graduation. So we'll have our transition matrix P that we just wrote out. That was 0.8, 0.2, 0.3, 0.7. And we'll start with an initial state vector, x0. So they did not give a donation. So that means the probability they gave is 0. The probability that they did not give is 1. So that's our initial vector. So that means that our next state vector, x1, is P times x0. So that's our transition matrix, 0.8, 0.2, 0.3, 0.7 times 0, 1, our x0, and we get 0.3.7. Okay, let's find x2 now. For x2, that would be p times x1, the preceding state vector. So that's 0.8, 0.2, 0.3, 0.7 times 0.3, 0.7. And we get 0.45, 0.55. Okay, let's keep going, get x3. Okay, we'll multiply p times x2. So 0.8, 0.2, 0.3, 0.7 times 0.45, 0.55. And we get 0.525, 0.475. If we were to keep going like this, we would get x4 equal to 0.563, 0.438. x5 is equal to 0.581, 0.491. Then x6 is 0.591, 0.409. x7 is 0.595, 0.405. x8 is 0.598, 0.402. x9 is 0.599, 0.401. x10 is 0.599, 0.401. You can kind of see what's happening now. Shouldn't surprise us that x11 is 0.600, 0.400. So it turns out that for all of the n that are greater than or equal to 11, xn is equal to 0.600, 0.400. Cool. So it looks like they're approaching that vector, which begs us the question, what about for example 1? Did they also approach a fixed vector? So let's write out that transition matrix. From example 1, it was 0.8, 0.1, 0.1, 0.3, 0.2, 0.5, 0.2, 0.6, 0.2. And we'll start with x0 equal to 0, 1, 0. Just to see what happens when we start with that vector, and we'll see if it approaches any vector. So we'll look at what x1 would be in this case. So we'll take 0.8, 0.1, 0.1, 0.3, 0.2, 0.5, 0.2, 0.6, 0.2, and multiply it by 0, 1, 0. So that gives us 0.300, 0.200, 0.500. And let's look at what the next vector would be. So that would be 0.400, 0.370, 0.230. Again, just multiply by matrix P. We'll get x3 equal to 0.477, 0.252, 0.271. And then x4 is 0.511, 0.261, 0.228. x5 is 0.533, 0.240, 0.227. x6 is 0.544.238.219. X7 is 0.550.233.217. X8 is 0.553.232.215. X9 is 0.555.231.214. X10 is 0.556.230.214. And X11 is 0.557.230.213. So for n greater than or equal to 11, it turns out we'll actually get xn equal to 0.557.230.213. So that's the vector they approach. Let's do another example. Suppose that we have a traffic officer assigned to control the traffic at the 8 intersections indicated in the figure. She is instructed to remain at each intersection for an hour and then to either remain at the same intersection or to move to a neighboring intersection. To avoid establishing a pattern, she is told to choose her new intersection on a random basis, with each possible choice equally likely. For example, if she is at intersection 5, her next intersection could be 2, 4, 5, or 8, each with probability 1/4. Every day, she starts at the location where she stopped the day before. Find the transition matrix of this Markov chain and use it to determine whether the state vectors approach a fixed vector. So let's say over here at 5, it means that she could go here, 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 or stay on 5. 4 different possibilities, each with equal probability 1/4. So how about we build our transition matrix? On the top, we'll have the intersection that she's starting out at, so that'll be our old intersection. And then on the other side, we'll have the new intersections. So first, the old intersections are 1 through 8. So let's number those. 1, 2, 3, 4, 5, 6, 7, 8. And then she could end up at 1, 2, 3, 4, 5, 6, 7, or 8. So these are our new intersections. And let's see. We'll start with number 1. So if she starts at 1, she could move to 2 or to 4 or stay at 1. So there's only 3 possibilities, so each one has a 1/3 chance. The rest have probability 0. So there's 1/3 probability that she stays at 1. There's 1/3 that she moves on to 2. There's 0 probability she goes to 3. And there's 1/3 that she moves on to 4. And then 0 for the remaining probabilities. Yeah, close enough. I'm trying to line it up, but not so easy. Okay, so for number 2, she can move to 1 or to 5 or stay at 2. So again, 3 possibilities, each with 1/3. So 1/3 that she moves to 1, 1/3 that she moves to 2, 0 that she goes to 3, 0 that she goes to 4, 1/3 she goes to 5, and 0 for the last 3. And next up, we have for number 3, could go to 4, or to 6, or stay at 3. So 0 possibility that she ends up at 1, 0 possibility she ends up at 2, 1/3 she ends up at 3, 1/3 ends up at 4, 0 at 5, 1/3 at 6, and 0 otherwise. Okay, next is 4. 4 could go a lot of different places. It looks like they could go to 1, 3, 5, or 7, or stay at 4. So there's 5 different possibilities, so each one has probability 1/5. So 1/5 that they go to 1, 1/5 going to, well, 0 possibility going to 2, 1/5 that they went to 3, 1/5 that she goes to 4, 1/5 at 5, and 0 possibility of 6, 1/5 of 7, and 0 possibility going to 8. Okay, next is 5. I'll just read it out. It'd be 0, 1/4, 0, 1/4, 1/4, 0, 0, 1/4. And then for 6, we have 0, 0, 1/3, 0, 0, 1/3, 1/3, 0. Yeah, I didn't do a very good job lining this up, but that's okay. So 0, 0, 0, 1/4, 0, 1/4, 1/4, 1/4. And last but not least, we have 8. We have 0, 0, 0, 0, 1/3, 0, 1/3, 1/3. And this is our transition matrix. Maybe you want to draw it a little bit more neatly. In any case, how about we start with state vector at 5. So we'll have zeros for all of the other intersections and a 1 at 5. And let's see whether this approaches a fixed vector. So we'll do x1, and taking this matrix, multiplying it by x, you can use a calculator if you want, you get 0, 1/4, 0, 1/4, 1/4, 0, 0, 1/4. Multiplying by our matrix P again, for x2, we get 0.133, 0.146, 0.050, 0.113, 0.279, 0, 0.133, 0.146, and so on. We can keep going like this. We could get to x22 and see that it would be 0.107, 0.107, 0.107, 0.179, 0.143, 0.107, 0.143, 0.107. And beyond this, all of the vectors actually, x23, 24, and so on, are all the same as x22 up to 3 decimal places. So as with the other examples, they do approach a fixed vector. For our next example, how about we let P equal the matrix given 0, 1, 1, 0, and x0 be 1, 0, and let's determine whether the state vectors approach a fixed vector. Because, we've already seen a whole bunch of examples now where they do, so maybe this one will break that chain. And in fact, if we square P, we get the identity. And if we cube P, we get back to P. So that means that x0 is going to be the same as x2, which will be the same as x4, because to get to x2, we multiply by b squared, which is the identity. To get to x4, we multiply by squared, which is the identity, and so on. So all of these guys are going to be 1, 0. However, the vectors x1, x3, and x5, in fact all the odd state vectors, will all be equal to 0, 1, because we just take x0, we multiply it by p, and then each one is multiplied by p squared, so they're all multiplied by the identity after that first one. In any case, we see that here we finally have an example of state vectors that do not approach a fixed vector. So it doesn't always happen. So a transition matrix is regular if some integer power of it has all positive entries. We'll use that definition to talk about when we have vectors that approach a fixed vector. So we have this theorem that says that if P is a regular transition matrix, so that means some integer power of it is all positive entries, so then we have as n tends toward infinity that Pn is given by this matrix of Q's, where the Qi's are positive numbers such that they all add up to 1. And then we could talk about the behavior of P and X as n tends towards infinity. If P is a regular transition matrix and X is any probability vector, then as n tends towards infinity, P and X tends towards Q, where Q is a fixed probability vector, independent of the n's, all of whose entries are positive. This brings us to our last theorem of this page, which says that the steady state vector Q of a regular transition matrix P is the unique probability vector that satisfies the equation PQ equals Q. In other words, you take that vector, you multiply it by the transition matrix again, and you still have Q. It doesn't change. You know, you're already tending towards Q, so it should make sense that this would be what you want to look for. So let's do an example and find the steady state vector from example 2. Instead of just multiplying out all of the all the state vectors by P over and over and over again to see what it approaches, we can calculate it by writing out what P was. Our transition matrix was 0.8, 0.2, 0.3, 0.7, and then we know that PQ equals Q, so that's the same thing as saying that I minus P times Q equals 0, or the 0 vector, rather. So we'll take 0.2, negative 0.3, negative 0.2, and 0.3. So all I did was make these guys negative, and I took 1 minus the diagonal entries to get I minus P, and then I'll multiply that by Q. I don't know what it is yet, so I'll leave that as Q1 and Q2, and I'll set that equal to the 0 vector. Alright, let's solve for Q. So this equation tells us that 0.2 times Q1 minus 0.3 times Q2 should equal 0. It also tells us that Q1 should equal 1.5 Q2. So that means that Q is equal to S times 1.51, right? I could just take some parameter, right? If Q1 is always equal to 1.5 Q2, then just some parameter times the vector 1.51 gives all of the possible values of Q. However, there is a restriction on this S, stemming from the fact that we know that Q is supposed to be a probability vector, which means that these two entries are supposed to add up to 1. So we can figure out what S is by dividing by the sum of those entries. So we'll take S equal to 1 divided by 1.5 plus 1, which equals 0.4. So if we scale these entries by 0.4, they'll have to add up to 1. So that means that the Q that we want will be 0.6, 0.4, which is consistent with what we determined experimentally. How about we now find the steady state vector from example 1? So this will take a little bit more work because p was a 3 by 3, but the same process holds. So p is 0.8, 0.1, 0.1, 0.3, 0.2, 0.5, 0.2, 0.6, 0.2, and we'd want to do I minus p times q is the 0 vector. So 0.2 minus 0.3 minus 0.2, 0.1, 0.2, 0.6, or minus 0.6, right? Oh, wait, I forgot to subtract for these. So 0.2, negative 0.3, negative 0.2. We have negative 0.1. Yeah, that's better. And 0.8 and negative 0.6. And then negative 0.1, negative 0.5, and 0.8. Okay, so that's I minus p. And we'll multiply that by q. We'll set those arbitrarily as q1, q2, q3. Getting ahead of myself over there. And then 0, 0, 0. Okay, so we multiply by 10 just to make things easier to work with. So I'll have 2 minus 3 minus 2 minus 1, 8 minus 6 minus 1 minus 5, 8. We'll reduce that. And we'll get 1 minus 3 over 2 minus 1, 0, 13 over 2 minus 7, 0, minus 13 over 2, and 7. So that bottom row isn't going to help us much, but the top two rows will. So we'll keep reducing. We get 1, 0, minus 34 over 13, 0, 1, minus 14 over 13, and zeros for the last row. That tells us that Q1 equals 34 over 13 times Q3, and that Q2 is 14 over 13 times Q3. So that'll be our parameter S. So we can have Q equal to S times 34 over 13, 14 over 13, 1. And again, we need to figure out what S is to force all of these guys to add up to 1. So S will have to be 1 divided by their sum. So that's 34 over 13 plus 14 over 13 plus 1. And that equals 13 over 61, which gives us a Q equal to 34 over 61, 14 over 61, 13 over 61. And in fact, that is consistent with what we got because it's approximately 0.5573, keeps going, 0.2295, 0.2131. Okay, let's finish up by finding the steady state vector from example 5. All right, so this one's a doozy because we have a ginormous matrix P. So I'll quickly rewrite that. Managed to do it a little bit more neatly than last time, but now I have to write I minus P. So that'll give me 1, 0, 0, 0, 0, see, 2, 3, 4, 5, 6, 7, 8, okay. I'm reducing it at the same time so that I don't have to keep writing this matrix. So 0, 1, 0, 0, 0 in reduced row echelon form. And let's keep going. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 0, 0, 1, 0. And then we finally have some action, -1, -1, -1, -5/3, -4/3, -1, -4/3, and 0. And then we set that equal to 0. Okay, great. So nothing from the last row as in the previous examples. What this tells us is that Q1 is equal to Q8. Q2 is also equal to Q8. Q3 is equal to Q8. Q4 is equal to 5/3 Q8. Q5 is equal to 4/3 Q8. Q6 is equal to Q8. Q7 is equal to 4/3 Q8. So we can write Q as S times 1, 1, 1, 5/3, 4/3, 1, 4/3, 1, and that's it. So let's make this a probability vector. We'll add up our entries, 1 plus 1 plus 1 plus 5/3 plus 4/3 plus 1 plus 4/3 plus 1. Put them underneath 1, and we get 3/28. So that makes our vector Q equal to 3/28, 3/28, 3/28, 5/28, 4/28, 3/28, 4/28, 3/28, which is equal to, up to 4 decimal places, 0.1071, 0.1071, 0.1071, 0.1785, 0.1428, 0.1071, 0.1428, 1071. Right, that's 8 of these guys. Okay, good. And that's consistent with what we saw before.